So we will go back again to the first slide. I mean, we need to work with those data pre-processing. And after that, we will try to go to, I mean, error bug propagation algorithm. I got a question last time that we need to implement it. And I did some simple implementation for it. Yeah. Yeah, so I got some phones. Ahmed? Hello, Ahmed. How are you? Oh, okay. So because I came late also, and I decided to start from the office. You cannot get access. How many people there? How many people there? Only two. Is it possible to just because I can come after the break, after the first break I will move. Okay. Yeah. Okay. Thanks, Ahmed. Bye, see you. So just maybe we need to start after 5 minutes. So can you please just I mean go through those slides until I mean we just need to have 5 minutes break because in fact the plan today to start from a lab. So I wish also if we can go there, if I can go there, because just a minute. Ahmed, you can stay there. You are there with student, master student. But I can come. I can come now and open it and work from the lab. Is it fine? I mean, the plan was to start from a lab if there is enough people. I mean, to start with from the lab. Okay. So just wait for me and I will come soon. Okay. Okay. Thanks. Bye bye. So sorry guys, we have a lab here in MCO, and we wish to start there I mean, from this lab today. So just after 5 minutes, I will be online. If you can wait for 5 minutes, just I mean you have the slides, so just go through it, and I will start after 5 minutes from the lab. Thanks. So I will stop sharing, but maybe you can stay within. I don't know if I stopped sharing. Maybe I can give. For example, to maybe to I mean Ravi, Masoud, Muhammad, for example, I can give one of you. I just want to make someone else as a host, so because we don't need we need to keep this one working. So I can select the first one in the list. Amir, for example, or Pure Nar, for example, anyone. Hello, everyone. I don't know because they told us how can we set up our cameras. So I hope that you can hear us. We will just fix the video because we have some cameras here. We need to fix it. We just have some cameras here. I don't know why it's not working, but did you try to use a phone before? This one? How can we know that this one is working or the camera?
How's the camera?
Mhm.
I've never used that.
You're not, can you repeat this? Yeah, we set up those cameras. I selected the microphone, but not the camera. I selected them. You see this one? This one? This one is not connected. Your default or we need to select camera, right? Your default microphone is changing. Okay, we have the microphone, but not the camera. So we cannot add those maybe from the setting we can, because there's a camera here which we need to use. Bluetooth printer, you know. I guess we can start using the camera here in my computer. We don't need anyways the camera, but we have camera here in the lab, but it's not working so far.
Now, I pressed on here.
Okay, for you know, is it about light or about camera? HDMI.
I pressed on because it was.
Okay. Okay, so. Oh, okay, now it works, by the way. It should. I mean, this one, it looks like. Look, it works. This camera is working, but I cannot get access. Okay, so we will start, and I mean, maybe with time we will know how to use this those tools. Can you see my screen?
Yeah.
Can you see?
No, we see your camera.
My camera, okay.
So,
Maybe is it really important?
you have to just press share screen.
Share screen is not working also. Okay, share screen, lecture number 5. Okay. So I hope, guys, that you can see my screen. Can you see my screen?
Yeah, it's good.
Okay.
It's good.
Okay. So now we will go for, I mean, maybe next time, maybe I can, I should switch off my camera. Okay. So today we will talk about data pre-processing, and I mean, we started this one last time. So last time we have been talking about okay. I mean, we have been talking about inseparable data set and separable data set. When it's inseparable, so can you change the next slide, or you cannot see?
No. No, yeah, now we are inseparable data set.
Inseparable data set. Okay. Okay. So I mean, data sets. There are two types of data sets: separable and inseparable. And when it's a separable, we can find the session line. a straight line, which can be used for dividing, for example, if it's binary classification problem, we can have those two classes. We can use one straight line for dividing the data sets into two. So this decision line, it's a straight line, and we can get this line using, I mean, a perceptron or adaptive linear unit, for example. So the equation will be omega x plus p equals 0. And we try to find, I mean, value of omega and b, for example, to find this line. But in some cases, so for example, this one, it's a separable data set. So it's easy to find a straight line to divide it. There is no overlap, in fact. So when it's easy to find a straight line or a plane, and if it is in three-dimensional space, for example, or higher dimensional space, we can call it its inseparable data set. But so there are some other data sets which is really very complex, like this one. It's inseparable, which means we cannot find one straight line to divide it into two different classes, for example. Sometimes we need to, maybe we need more complex shape of decision boundary. We need to generate more complex decision boundary to divide the data into two sets. So last time we worked with this example XOR, because XOR it's one of the most important examples, because in 1940 something, when they started using those tools, for example, when they invented a perceptron and the perceptron learning rule, they got this problem and they tried to solve it using a perceptron, and it was impossible. So they said, machine learning or artificial or neural network, it's a fake tool and it cannot be used for. And in fact, it stopped them for a long time. They couldn't use a perceptron for solving complex problems, and at that time they had huge, very high ambition and expectations, and they couldn't fulfill those expectations, and it was really a problem. So this problem, for example, we have two classes, it's one class and zero class. The data set is very simple, right? But if you need to find a straight line, maybe you can select one straight line in this direction or in that direction. It will be impossible, in fact. Each time you will get maybe accuracy, maybe maximum 75%. Because if I selected the straight line like this, for example, this one, it will be correctly classified. This one, it will be wrongly classified. So we can say that the accuracy will be 75%, right? And so we will not get accuracy higher than this using one perceptron. This type of problems, we need to get, in fact, two straight lines. We need to get two decision lines. If we can get two decision lines, all data points which will be located between those two lines, it will be defined as one class, and the data points above and below it, it will be another class. So how can we get this one? I mean, in the break, I will get some, we have some stuff here. Can we use this one?
Yeah.
So, we have a camera here, but we will fix it after the break. Maybe you can ask people from IT to help us. Because we can follow up and back using this camera.
There will be thing to turn your camera more.
Okay. Okay.
Yes.
Okay. Very good. Thanks. So now if we have this kind of problem, it's this XOR problem. So if we need to draw it, So for example, we have this kind of problems. So we need to find a decision line. So we have here one point. We have here another point. It's a class. Can call it +1.
Can you make this the two?
Okay. So this one it's a +1. This one it's a +1. This one it's a negative or 0, for example. This one it's a 0. We can make it like square, for example. So this kind of problem is inseparable, which means we cannot find a straight line to divide. We need two lines. So we can find one line here and another line here. All data points between the two lines will be classified as 1. Above and below it will be 0. How can we get this one? We can use two perceptrons. We have here two inputs. I call it x1 and x2, for example. We have all those connections. So this one will generate one line. This one will generate another line. And after that, we need one to make the decision, to combine decisions. So finally, we will have this one. So y now will be maybe 1 and 0, for example. But we have one perceptron which will generate one straight line. The other one will generate the other line. And the third one here in the output layer, it will just combine the decisions between, because we need to make ending between the decisions. Because in fact, when we have this line, all data points above it, it will be one class. All data points below it, it will be another class. For the second line, all data points above it, it will be one class. Data points below it, it will be another class. So we need to make ending between those two decision boundaries. How can we make this ending? Using the third perceptron. So in this case, we can make decisions, because what is important for us in classification to make decision, yes and no. This problem is binary classification problem. So we need the output to be 1 and 0, right? So how can we make this? Using the third perceptron. And if you can look into it now, using this structure, in fact, it's not a perceptron anymore. It's straightforward and correct? Because
We have more than one perceptron. Because this is, you have more than one perceptron.
Yes, because we have now it's 2 layers. We have an input layer, we have a hidden layer, we have an output layer, right? If it is a perceptron, we have only perceptron, it's just 1 unit. And we use it for and or, for example, or in many other programs, even in MNEST, yes.
They are complaining that they can't see the red marker, or they can't see anything.
We will fix that because we have a camera here, but we will fix it maybe in the break, right? So I will go back here, if you can see me here. So we have here 2 classes, the blue class and the red class. The blue class, it's classified as 1, and the red is classified as 0. This problem is inseparable, which means we cannot use only one straight line to classify it. At least we need 2 straight lines. We need 2 lines. How can we do it? We can do it using 2 perceptrons. One perceptron for generating this line, and another perceptron for generating this line. Correct? So we will have one perceptron for generating one straight line, another one for generating a second line. All data points above this line, it will be classified as 1. All data points below it, it will be classified as 0. For this line also, all data points above it, it will be classified as 1. And all data points below it, it will be classified as 0. Now we need to get intersection. We have 2 decision lines. We need to get the intersection between the decision boundary. Yeah.
They can't hear the sound very clearly.
Clearly?
Yeah, the sound.
Okay.
Okay, if you want to use your laptop.
Should I use my laptop sound?
Just use your line.
Okay.
Yeah.
So maybe we need another screen, in fact, because it's not easy to. But I don't know.
Yeah, but you can still use the cut screen.
Okay.
To switch, but we have to switch so
Okay. So I can just change it from here. Now we are using. No, we need to use this one. Is it better now? Because now I have been using my computer, which was not
They
correct.
said yes.
Okay, now it's fine.
Yeah, they said yes.
Okay, now we will check also the camera. Maybe the camera is working. Because we should use
Integrated camera, the other one. Can you go up?
no, not integrated.
No,
because
can you choose the other option in video? Go up, little, yeah. Change the option. That's the only one.
only one, but we should get this one here, in fact.
That's the only one connected anyway to the laptop.
No, yes, this is the one which is built in, but we should use this one, in fact. So I don't know why can we can't. I don't know if it is on or off, in fact. No, it works now. Do you see? So, but it's not connecting to that. So, but anyway, it should be at least maybe advanced.
Video.
No. I have no idea if I should. Also. Okay, we have the sound from. So it's only the camera. We don't know how to how to connect to this one. We should have a camera here. We should have the other one. Okay, so the problem now, we will have two decision lines. We need to combine it. We need to find the intersection between the two. How can we find the intersection? We can find it by using the third one. So in this case, we have three perceptrons. So we are organizing it as a feed-forward neural network. We have an input layer, we have a hidden layer, and we have an output layer. And this is very simple one, in fact, right? So, but the same problem, you can solve it using only two. So we can use one hidden layer with one perceptron and the output layer with one perceptron. So, I mean, we did that before. I mean, in the last years, we tried to find the most sample for solving it. So in this case, we are working with the data as it is, right? And we build feed-forward the neural network. We have, now you are free. You can just increase the number of units in the hidden layer. So if your data set is more complex, in fact, you can just increase the units in here. Because it will, now it can make this simple mapping between inputs and outputs, and it will generate a nice decision line, and it will be able to solve our problem using this feed-forward neural network. We cannot use perceptron anymore, but if you want to make it more complex, you can just play with the structure of your feed-forward neural network. You can increase the number of units in the hidden layer. You can increase this one, 3, 4, 5, 6. If you want to really to make it more complex, you can add one more hidden layer. Right? So now we have a feed-forward neural network. It's not a perceptron anyway. So now we can plot the, yeah.
For example, if we add more nodes or more hidden layers, the idea is like all of them has to be grouped into one final perceptron.
Yes, because this is a decision. We have only one here because the decision it's just 1 and 0. So if we use the Gaussian, for example, at the end, the decision will be 1 and 0, right? Now we cannot use hard limb anymore. We need to use Gaussian. So if we use the Gaussian activation function, the output here will be probability. It will be number between 0 and 1. So if it is below 0.5, it will be classified as 0. If it is numbers greater than 0.5, it will be classified as 1. So at the end, what we will get here, it will be the probability. What is the probability that this one belongs to 1 or to 0, for example?
If it's multi-class, then if it's multi-class, then we would have more nodes.
More, yes, correct. Of course, if you have, for example, class 1, class 2, like MNIST, like Iris dataset, we have 3 classes. So in this case, I cannot play with only one output because I have 3 classes. We can use one hot encoding. And in this case, we need to get in the output layer, we need to get 3 units, right? Because I need to have 3 decisions. And it will be also the probability, and the summation of the probability will be 1 in each one. One hot encoding, we have 3 classes. For example, class 0, class 1, and the class 2, for example, we need to convert it into one hot encoding. So the output will be 3 values. For example, 1, 0, 0 if it is 0, and it will be 0, 1, 0 if it is 1, and it will be 0, 0, 2 if it is class number 2. So one hot encoding, it's a smart tool. In fact, it's magic because it can help us, in fact, to make the problem much easier. So instead of getting a number here between 0 and 1, and after that you need to convert it into 1 and 0, you can just play with one hot encoding. And in this case here, we need to use another. We will add another one here. So we will just add another one here, right? So we'll just make this one. If you will use one hot encoding. If it is this class, it will be 1, 0. If it is this class, it will be 0, 1, right? It will be much easier, in fact, for the neural network to train. So now we are moving from a perceptron to a feed-forward neural network. So as I told you, I mean, there is a pipeline in machine learning which we need to follow. If you need to work to solve a problem, we need to start with pre-processing. I mean, try to visualize your data, try to normalize, standardized. And I mentioned that before. Why do we need to do this? It's because of the activation function. Because our activation function, if you use sigmoid, for example, so it will squash all higher values into 1 and all our values into zeros, right? So this squashing impact, it will hide lots of information, in fact. So we collected data, and the data has lots of variations. For example, if you didn't normalize your data set, most of the data will be squashed. It will be chopped out, right? It will disappear. So we will not keep those variations because all higher values. So how can we explain it? It's for the activation function. So if we are using this kind of activation function, right? All higher values will be converted into 1. All lower values will be converted into 0. So we will keep only very small part here, right? But if you want to be sure that all data are reserved and used, we can normalize all our data sets. When it's normalized, it will be usually between that part. So now we are sure that all values are represented. So normalizing the data set or standardizing it, it's very, very important. So after collecting your data set, you need to visualize it to understand how it looks like. Maybe you can use some statistical tool, for example, to find some correlations, because maybe I have some repetitions and stuff like this. We can use some statistical tool to select the most important features to play with, standardized or normalized. And after that, select a model. You need to select a model. Which model should we use, right? It's based on the problem. Is it a binary classification problem? Is it multi-class classification problem? So model selection is very important. After that, you need to divide your data into a training and testing. Why do we need to do this? Because after training my model, I need to test before producing it, before deploying it, before production. Because if you will build a model for a company or a hospital, for example, you need to check it first. And after that, you will deploy it. You will just say, okay, my model works fine, you can use it. So we will divide the data into one part for training, one part for testing. And the part for training will be used for adjusting the model weights or parameters. And the one for testing will be used for testing my model. In the testing, we need to get something like this one, confusion matrix. So the confusion matrix in classification problems, it's very important because it will show us how many classes are correctly classified, how many are misclassified. So it will give us impression about what is the performance of my model, because maybe my model works fine in all classes except one. So in this case, we need to build maybe in samples, you put in sample, we need to build a model for the other one. And so this one, it will help us, in fact, to understand many things, this confusion matrix. So confusion matrix is very important. But confusion matrix, we use it for only classification problems. If it is regression, we cannot use confusion matrix, right? So this one, for example, in this problem here, we have 2 classes. So we need to know how many 0 classes are classified into zeros. How many 1 classes are classified into 1. So this is the true classes. This is the predicted classes. If numbers, we need to maximize numbers across this diagonal, because the other numbers across the other diagonal, in fact, it's error. Because this one, in fact, it's 0 classified, misclassified as 1. And this one, it's 1 misclassified as 0. So we need to minimize numbers across this diagonal and maximize all numbers across the other diagonal, right? And from this confusion matrix, we will get many things. There are lots of numbers which we can get from the confusion matrix. So the pipeline which we need to follow, first, upload your data or collect your data, upload your data, visualize it, try to work a little bit with your data to simplify it, for example. Use BCA, for example, principal component analysis, to select the most important features. And after that, model selections, training, testing, correct, evaluation. In the evaluation part, we need to get the confusion matrix. And after that, you will what is the type 1 error, what is type 2 error, what is recall, what is precision. So you will get all those numbers. You need to put all those numbers in a table, right? And after that, if you are building it for a company, they will check it. And after that, it will go for production. But you cannot just do it because some people, he can just collect the data, train the model, and just say, okay, my model is accuracy is 99.9%. Is it true? No, maybe not. Because maybe it's true in the training data set, but for the testing, we don't know how the model will perform in the testing. So it's very, very important to divide my data set into one part for training, one part for testing, to check the performance, because maybe my model overfit my data, right? It memorized it. So it will has very good accuracy for the training data set, but not for the testing data set. So we need to discover this. How can we discover it? We can discover it from the testing sets. But remember, before dividing your data set, you need to shuffle your data set very well. If it's not shuffled, you need to shuffle it. Why we need to shuffle it? Because I want all my classes to be represented, equally represented in the training set and in the testing set, right? And in Python, we have this function. It's a train test split. We have Spotify. So we can get, I will show the code. So, okay. Yes, so we have this, okay. don't see, it's not here, and I don't know. Do you see the next slide code? You can see it. Okay.
No, I cannot see. Yes, yes, yes.
Why it's not here?
You cannot see it on the screen.
Because the slides.
Hmm?
I think what you are following is the slides, because there are two things we can see here, the video and the slides.
Okay, but I mean, when I change it in my computer, it's not here in the screen.
It's in the share screen, I can see, but in this.
Yeah.
Yes.
The video recording
Yeah.
you cannot see.
Hello, Ibrahim.
Hello,
Good morning.
good morning.
I was saying, you didn't tell me today class is, we can come over class and use. And also you didn't send for me the link of class.
He doesn't have access to Blackboard.
No,
I
but-
don't
but-
have, I
Yeah,
don't have
you-
access to it.
Yeah, correct. But you have a link. You are with us now, correct?
Yes, at the moment, one of my friends sent for
I
me
sent
just.
him the link.
But I put him in the mailing list, in fact.
You didn't send him an email. It was on
No,
Blackboard.
no.
Oh, sorry. Yeah, correct.
I sent him the link.
Yes, sorry. It's because I didn't send the link by email. I thought that all people are. Sorry, we will fix it next time. Yeah. And we will
At
fix.
at the moment, it is possible to join your class?
Yes, we are in MCO in 6th floor.
Yeah.
Yes, we are here. So you can just join us, please.
Okay. Thank you.
And we just started late, by the way, so don't worry. Yeah.
6th floor of main building, yes?
6. Yeah. In
Floor to 6B.
6B.
6B. Okay. Thank you.
And you have to text the receptionist to activate the card for 6B.
Yeah. And ask the reception to just give you access. We are here anyway. You can just go to the 6th floor and we will open the door for you.
Yes.
Because at the moment I'm in a K building.
K building, Kroskop.
Yeah.
No, you need to go to MCO. You need to cross the road to the other side.
Okay, thank you.
You need to go from the tunnel to the other side.
Okay, thank you.
Yes, thanks. Yes.
Tell them that is need ask permission to come in.
Yeah.
So now it's the one which we are sharing, but it's not the one which is displayed here. So, okay, maybe we need to take this one here, right?
That's nice.
Okay, so because it was extending the screen.
Can you maximize the screen?
Yes. Okay. So if we need to build this model, we need to build our data set first. So we have X and Y, we defined X and Y. We need to define a model. I used the multi-layer perceptron from sklearn.
They can't see.
They can't see it. They see only this.
Okay. Sorry for this today.
It's okay.
I apologize because it's the first time to use. We need to just duplicate and just close
There
this
we
one.
go. Now I can see.
Yes.
There we go.
Yeah, now they can see it in your screen.
You can see it.
Yeah.
Okay.
Yeah, they can see it now.
Okay.
Now
So
it's working.
Now it's good. Yeah, perfect.
Yeah.
So this is the code. For example, if we need to try this example, we need to generate our data set, right? So this is my data set. It's nb.array. It's nb array. This is the model which you need to use. So the model this time, it's multi-layer perceptron classifier, because this one, it's multi-layer perceptron. Now, we will not call it a perceptron because it's not a perceptron, but it's multi-layer perceptron. It's layers of perceptrons. So in sklearn, they call it multi-layer perceptron. In some other places, they call it feed-forward neural network. Any name, no problem. We know the content. So it's MLB classifier. We need to select the activation function, number of iterations, the size of the hidden layer. We need to select 2 units in the hidden layer. So when it's only 2 here, it means you have only 1 hidden layer. And this number, so if you need to add another hidden layer, you can add it here. 2, 3, 5. So each one, it will be one hidden layer. And this number will be number of units in each hidden layer. And the solver, it's the optimizer, which we will use. Model fit, Y predict. Of course, the data set is very small. I didn't split it to training and testing. And after that, I will check the error. This one, it means number of cases which is not equal. Number of cases, number of classes which are misclassified, because this is the error. So this number, when Y not equal Y predicted. So we need to count those numbers. So this is the prediction error, and after that we will try to plot the decision boundary, and we will try also to get the confusion matrix. So now I need to extend it to a larger problem, XOR problem. We will try to make it more complex because I need to find this complex decision boundary. So I generated those data points. Those data points looks like XOR, correct? This one it's 1, 1, 0, 0, correct? We have 2 classes. This one will be +1, +1, 0, 0. So the decision line now, it will be more complex. You can, when you are generating it, in fact, you can control how much overlap, right? So I used here, in fact, it's a k equal 100. So in each cluster here, it will be 100 points. This is the offset of classes, the distance between classes, because I need to get some distance. I need to make it more simple. And I just generate all those numbers by random. And I try to add the offset here to generate this one. So adding a q minus q. So I just try to generate those data points, which looks like an XOR data set. After plotting it, we need to find a model to classify it. We will use MLP, the same. It's the same, it's MLP the same, but the hidden layer, it's much larger now. So I used here 20 units in the hidden layer, and we try to do it. So each time when we run it, we can find a different and the more complex decision boundary. So now we have this decision boundary, which we classify that into 2 classes, right? So the one it's in the middle, it will be 1 class. This one, yellow one, it will be 0 class. So now we can generate more complex and more. So when you increase the number of units in the hidden layer, you will generate more complex shape, in fact.
Okay, so it's not even linear, it's polynomial, I guess.
It will be very, I mean, it's hard to describe it as because we cannot, it's not X omega. Indeed, each perceptron will contribute by X omega plus B, but at the end, this is the total decision boundary, which is really complex to describe. So it's hard to find an equation to describe it. So how can we draw the decision boundary? We can just generate all data points between maybe minus, this one, it's between -1 and 1. So we will generate all data points. We will create a grid. So I will generate, for x1, I will generate all data points here from maybe -1 to +1 with small step. And I will do the same for x2. And I will generate a grid. I will use mesh grid. So we will cover this one with a grid. And I will apply each point to the model to predict which class. So this is how can we do it. So this is a decision boundary. First, we will generate x1. So x1 will be x1 minimum to x1 maximum. So I will generate all data points between x1 minimum and x2 maximum with a step. The step will be 0.01. And I will do the same also for x2. Here, x1 and x2, they are the same, they are equal. And I will use mesh grid to generate a grid. So we will have a grid. And I will apply the model to each point of the grid. So I will just send all those values to the model to predict which class. So now each point will be classified as 1 and 0. And finally, we will plot it using this contour F. So this is how can we do it. If it is a perceptron, it's easy to use omega x plus b equals 0, right, to generate the decision line. If you know x1, I can find the equation for x2, and I can just plot the decision line. But when it's more complex like this one, we will generate the grid, and we will send all those data points to the model to predict at which class. So this one, it will be grid. So this point, is it 1 or 0? This one, is it 1 or 0? This one, is it 1 or 0? This one, is it 1 or 0? So I will generate a grid, and I will send all those grid points to my model to predict which class it belongs to. So now we can have it, and after that I will get the confusion matrix. So I have many cases. In fact, it's 200 cases, if you can see it here. 200 cases class 0 and 200 cases class 1. And as you can see here, the accuracy is 100%, right? Because 200 cases of 0 was classified as 0. 200 cases which is 1 was classified as 1. So the accuracy is, but also this work is not correct. Why? Because I used the whole data set for training my model. We didn't divide. You should divide, right? If you run it each time, you will get different solution because we didn't use random seed. If you can remember here, we didn't define a random seed. So each time you run it, you will get different decision boundary. But also the accuracy will be roughly 100%, right? So you can play with the model. You can add one more hidden layer. You can, for example, simplify this one, maybe 5 units in the hidden layer, or 10, for example. You can just simplify it and you can play with it.
Sorry to ask you, in this algorithm, we haven't used any data set. We are just generating our own data set.
Yes, we are generating it. Yes, it's artificial data set. We just generated it. But also in Python, in fact, we have in sklearn, we have lots of data sets which can be customized.
Yeah.
And those kind of data sets are very useful because, I mean, sometimes you are developing a new algorithm, for example, and you want to test it with a standard data set, not something from real life, because you need to compare the performance of your model, your algorithm with other people. So how can we do it? How can we do those comparisons using a custom data set? Right. So we have some like Makeplups. Remember it?
Yeah.
So it's something standard which we can just use for generating a data set for testing our model. So the other, I mean, when we have been working with this example, we just used the data set as it is. We have been working with the raw data, right? And then when it's raw data, it's really complex. Do you see? We used one hidden layer and the 20 units in the hidden layer. So the data set was simple, in fact, because we have two features. We have X1 and X2, but to classify it, we used a very complex model, right? Can you count how many parameters are here in this model? How many weights? How many weights in this model here? How many omega value and bias? How many omega and p? How many parameters?
Multiplied by the number of features.
We have one hidden layer, 20 nodes.
20 nodes?
One hidden layer.
Yes, one hidden layer.
Multiplied by the number of features.
Number of features?
Plus 20 for bias.
Yeah,
20 for bias, correct. So it will be 20 times 2 plus 20. So it's 60 for the hidden layer. For the output layer, how many?
One bias.
One?
And two weights. We wait for it.
No, it's not.
Wait, right?
No. It's similar to this one, right? But here we have 20. We have 20 units. So in fact, it's 1 times 20, correct? Number of weights plus 1 bias, correct? Right? Okay. So we have this in this example here. We have one hidden layer, and in this hidden layer we have 20 units. 20 units. We need to find number of trainable parameters. So I just need to draw it. Yes. So I mean, in this example, we have we have one hidden layer which has 20 units. We have two inputs, x1 and x2. And in the output here, we have only one. So this one is connected to the 20. Those two are connected to the 21. So this one, 1, 2, until 20. So number of weights here, it will be how many weights for this one? It will be 20 times 2.
Yeah.
So this one will be 20 times 2 plus 20 bytes. Correct? And how many here? How many weights?
20 times 1.
20. 1 times 20
Plus
correct? Plus
Plus one.
Plus one.
Divided by us.
Yeah, correct. So it will be 1 times 20 plus 1. So this is one, it's 21. This one, it's 60. So in fact, we have 81 weights, weight value and bytes. 81 to solve this problem. We have two features. We have x1 and x2. And really, this model is really very complex. And you can see, because we have this one, it's a really very complex one. And we cannot generate this one using a simple model. We can generate this one, in fact, using very complex model. And the model is really complex. We have 81 parameters, right? So now we need to simplify it. Is there any way to simplify it? Yes, if we can work with the data pre-processing, we can simplify it using feature construction, feature selection, and so on. So how can we do this? So this is my original data set. This is x1 and x2. I mean, in feature construction, there is something called interaction and higher order features. Higher order features, which means I can use, for example, x1 squared, x2 squared, x1 cubed, x2 cubed, x1 squared plus x2 squared, and so on. So this is a higher order features. You can use the interaction. What is interaction? Interaction, it's multiplication. So x1 times x2, x1 times x2 squared. So it's a different combination. You can try all possible combinations, right? And you can use statistical tool like find correlation coefficient. You can find which one is best when you from those generated features. So in this example, we have x1 and x2. This is the original data set. Okay, now we will try to find a super feature which can help us to make the problem much easier. So now I plot my data x1 against x1 times x2, right? When you look into this data, this one it's plus, negative, negative, right? Imagine I'm multiplying now. So this one it's plus. So this one it's a plus 1 times a plus 1, it will be plus. When I use x1 times x2. So plus times a plus, it's a plus. This one here. This one it's a negative times a negative. When it's negative times a negative, it's a plus. Now it's moved up, right? This one it's a negative x times plus y. Negative times a plus, it will be negative, so it will go down. This one, it's in fact, it's also plus times a negative, so it will be negative. So when we use x1 times x2, the data will change, right? So instead of plotting x1 against x2, it will look like this one. But if you will plot it x1 against x1 times x2, it will look like this one. So all 1 classes goes up, and all negative 0 classes goes down, right? I hope that I got my power cable. So yes. So now when we plot x1 against x1 times x2, now it's easy to find a straight line to separate those 2 classes. You can find just this blue line, right? This blue line, in fact, I didn't plot it by myself. I got it by a perceptron. So I got this blue line by a perceptron. So now we can, when we use x1 against x1 times x2, it becomes more easy to solve. I just need 1 line, and all data points above it will be class 1, and all data points below it will be 0. So feature construction or working with data is very, very useful. So I just did it. I used a perceptron, and I used this parameters. And this is model coefficient, model intercept, and I trained the model. It's the same data set which we used last time. We solved it using 81 weights. So, and I just repeated it using a perceptron, but this time I'm using x1 as a feature and x1 times x2 as a second feature. So instead of working with x1 and x2, now I'm working with x1 with x1 times x2. x1 times x2, it's the interaction, it will consider the interaction between features. Now we can solve the problem, and I plot the decision line, and I got this line using a perceptron. So it's a huge. How many weights here for this model first, before your question? How many weights? For this?
Only one?
No, it's a perceptron.
Ah.
Yeah, it's a perceptron, and this perceptron has two inputs.
Yeah.
So one is x1, one is x1 times x2, and the output is y. And we have here bias. So how many weights? How many parameters here? Three. So two weights, omega 1, omega 2, and a bias. So it's a 3. So can you imagine? Can you compare between the two models? So we solved the same models, but this one was 81 parameters, this one was 3. And then once the number of weights decreases, number of parameters decreases, the chances to overfit will decrease. Your model will take less time for training. It will be easy to understand it and to just. There's something called explainable AI. It will be easy to explain it because now we have a decision line which is an equation. If you want to implement it in Raspberry Pi or any, it will be easy because the model is simple now. But this complex model, it needs processor, big memory, because it's 81 parameters, so it's really more complex. And then when the model is more complex, the chances to overfit will be much higher, right? You need more data to adjust to those weights because I have 81 weights. And I have 400 data points. So we need more data to train the model, right? And also chances to overfit would be very high. But when we simplify the data set using those feature construction, life will be much, much easier. So you need to spend the time with your feature and try to look into your features first and try to simplify it.
In this exercise, we haven't used x1 squared or x2.
No, we didn't. Because example, x1 and x2 is okay for this example.
And the second thing, what is the reason behind calculating the number of parameters? Why are we doing it?
No, it's just to show you the complexity. Because when we work with data pre-processing, it's a very important step. And people used to spend maybe 60% or 70% of their time working with the data before building a model. Because you can build a model and you can just run your computer and it will run for weeks. Maybe the accuracy would be really very bad, right? Maybe 70%, 80%. But if you can spend some time really and try to look into your data, try to simplify your data, it will save lots of time for development. Because the model will be much easier and it will be easy to explain the model to people. For example, if I'm building a model for a company or for a hospital, for example, it's important to have a simple model which help you to explain it for people, how the model works and so on. So working with data construction, feature construction is very, very important. Now it's not a problem because in shallow learning we have 81 parameters, but when you go for deep learning, for example, maybe this number will be millions, maybe 5 million, 10 million, 20 million, 50 million weights. So imagine how much GPU you need, how much time you need to train your model, how much data you need, right? Because if you have a model, complex model, you don't have enough data, right? The model will underfit your data. It will be, the accuracy will be really very bad. It will be impossible to improve it, yeah?
There is a comment here that when you have higher order features, then it's difficult to show it by a graph.
Yes, correct. This is a very good idea also, because, for example, imagine that this program you have 10 features, right? You have 10 features. How can we draw it? No, maximum we can plot 3 by 3 in 3-dimensional space. So one way for doing it is to try to select the most important features for visualization, because if I have 10 features, I will not be able to plot it. Do you remember Iris dataset? We have 4 features. And if we need to plot it in 2-dimensional space, we select 2 and plot it with, so to make it easy. You can select 3, for example, to plot it in 3-dimensional space. But which 2 should we select? We do it by random now, right? We just select 2 and plot it, and we can see that only 2 will be enough for classifying it. But if you can select the most important features, so there are some techniques for selecting the most important features Or we can do something called dimensionality reduction. We can use principal component analysis or autoencoder for dimensionality reduction. Because if you have 10 features, maybe I need to select the most important 3 features. So I can build an autoencoder, for example, to select the most important 3 features. The autoencoder will make some encoding and decoding. So I will select a coded version, encoded version of my data, or reduce the set of my feature. So instead of working with 10 features, I will work with 3. So it is the same here. If you are building a model, and if you will use, for example, 50 features here, the model will be really very complex. Because if I have here 20, it will be 20 times 10. If I will use 20 features, it will be 20 times 20, right? So it will be more complex. So if you can reduce the set of features, and this reduce the set will carry the same amount of information. The most important, how much knowledge we have, right? How much variations. So the most important to select is the features which carry most of the variation in my data set. Because as you know, when we're collecting data, for example, you have sensors, you have cameras everywhere. Maybe there are some redundancy, some noise. Maybe I have 2 sensors who are collecting the same data, for example, the same knowledge. Imagine in the bank, for example, for a credit card system, for example, we collect information. Maybe they take the age and years of experience. Maybe age and years of experience are correlated. So maybe I don't need to use both of them. Maybe one of them will be enough, because both of them carry the same amount of knowledge, the same amount of information. So why should I send the same amount of knowledge from different source to my model? So maybe one is enough. So we can use principal component analysis to try to find a superior feature which can simplify our life and can make my model more simple. And it's for visualization. So in fact, the dimensionality reduction can be used to simplify your features, to make it easy for you to visualize your data, and at the same time also to simplify your model. And remember, when the model is simple, it will be more efficient and easy to train. It will be more difficult to overfit and so on. So feature construction or principal component analysis, dimensionality reduction, very, very important. Very, very important. Yes. You have an example, Emir?
No, I have a question. If we use this multiplication, isn't it possible that we would lose some data, lose some information? Not here, but in general. Like the scale of the 2 features may be different. So if we multiply them, we would lose some information.
But when you multiply it, maybe you get more. Maybe you will lose. If you will lose something, just ignore it. So if you multiply it and you feel that okay, I mean there is no benefit in fact from multiplying x1 and x2, so just it's a trial and error, because this is my original data and I try to simplify it. So if I'm working with it, my data will be in column, right? So the first feature it's x1, x2. I will try x1 times x2. I will try x1 squared. I will try x2 squared. X times x1 squared. X2 times x1 squared. Right? So I will try all different combinations, right? And I will generate all those columns, and I can use, for example, find the correlation coefficient, or I can send all those features that will be in principal component analysis to select the most important ones. So they call it feature construction, and we will construct the one or keep the one which really useful for us, and we will ignore the rest. So if you cannot see any value from getting x1 times x2, just ignore it and try something else. But when we have those multiplications, we consider interaction between features. Yes, Ahmed?
No, just asking, for example, in practical, in industry, for example, can you assume that you have hundreds of features, like we are working with digital data or big data, hundreds of input features. Is there like an advanced algorithm to select these features, or normally we just feed them and we work for the problem as a black box?
No, you can, because it's very important. If you have 100 features, you don't know which one is important for us, right? So there are algorithms for feature selection. It will give you amount of variations which each feature carry, for example. And I can say I need to select the most important 6 or 10 features. So it will give you the most important 10 features. We will have an example maybe next week. You can use also principal component analysis. So in principal component analysis, it will transform those features into another set of features, and you can select and it will sort it. So it will be like eigenvectors and eigenvalues, and it will give you the highest eigenvectors with. It will sort it also from high to low, with eigenvalue. Eigenvalue, it will represent variations in my data set. You can select the first 5, the first 10, for example, and you can try to train your model. If the accuracy is fine, you can just keep it. Otherwise, you can try the whole data set, right? Yes, we will try it. When in fact, when you use BCA, for example, we lose some information because we transform the data from one dimensional space to another dimensional space, correct? And we select a subset. Maybe this subset, it will carry maybe 90% of the variations, not 100%. Because if you want to keep the 100% of variations, you need to keep the whole bunch of features. But when you select in principal component, maybe the first one will carry maybe 40%, maybe the second 20%. So if you selected 5 or 6, maybe the total variation will be like 90%. It will carry 90% of the knowledge of your data set. So you will lose some information, but it's a trade-off. But for simplifying your model, maybe simplifying your model will be more advantage for yourself, for your problem, right? So if I'm using the whole set, I will keep all my data set, but the price or the cost will be building a very complex model, which might be impossible to train, or maybe it will overfit. So we will try to simplify the feature. So you will lose something, but you will win something else. So it's a trade-off between complexity and the amount of information which you have. And all time I have an example, for example, if someone did a crime somewhere and people are collecting information, I mean, police are just meet witnesses and ask people for information. Maybe you will meet someone who will just give you too much details, too much information, which is not important. It will make the police more confused. So maybe if you have the whole set, your model will be confused. You will have some noise, but we try, if you will use BCA, for example, you will work with a reduced set. Maybe this reduced set, you will lose some knowledge, but the model will be more efficient. So, but we will have an example in BCA and autoencoder also for dimensionality reduction. So,
please, in feature engineering, if you come up with new features, is there any requirement that the new features have to make sense practically?
Not in practical, yeah. And also, yeah, this is a very good question. Not in practical, but it's for the problem,
okay,
right? For the problem. If it will make, because in machine learning, we try to map inputs into outputs, right? So I don't care about the physical meaning of x1 times x2,
okay,
or x1 is 2. We don't care about this. The most important is that it carries some variations, lots of variations, and some more knowledge, and it will simplify my data set for training. But we don't care about the meaning in physical life. And it's the same in BCA, for example. In BCA, maybe the input features, it's age and income and so on. The output will be something different, right? So when we use BCA for making this transformation, the features which will be used as a principal component, it will have no meaning, in fact, in physical life. So maybe the input, it's age, it's income, it's gender, and so on. The output will be something totally different, right?
What is BCE or PC?
It's BCA, it's principal component analysis.
Yeah, that's what's everything.
Yes.
Yeah.
Principal component analysis.
Yeah,
So the second example, it's this one, for example. I mean, we did that also last time, and I mean, it's inseparable as well. This is an example, and we generated it using this make circles. This make circles, it's from a scalar. So it's the same. It's a data set which can be generated. So you can decide here how many samples, how many noise, I mean the amount of overlap between classes. It's a binary classification problem. So the red one, it's a +1, and the blue one, it's a 0. So all data points which are here, I mean all these red data points, it's just a class 1, and the blue, it's a class 0. How can we classify this one using a straight line? It's impossible. It's impossible to plot a line here. I can plot a line here, but I don't know how much accuracy. So you see, maybe the accuracy will be 50%, 50%, right? Correct? But it's impossible to solve it using a perceptron. We need to, so how can we work with this one? We also, I mean, remember this one, we plot x1 against x2. It's the same. We can go back again also to feature construction. Is there any way to construct a new feature, which will be a super feature, and it will help us to classify it easily? So this example, it's very common. So I used here a logistic regression. and but I selected a new feature, a super feature. I selected x1 squared plus x2 squared as a new feature. So now I have, so my data set was x1, x2, the two features. Now I generated a new feature, which is x1 squared plus x2 squared, right? So if we will use a perceptron, it will be like this one. It's x1, this one is x2, this one is x1 squared plus x2 squared. And this is y, right? This one multiplied by omega 1, omega 2, omega 3. We have here bias, right? So the model here, I used, it's linear regression model, linear, not non-linear, it's just linear. So, but I used the higher order features, x1 squared plus x2 squared. So imagine that omega 1 squared equals 0, omega 2 squared equals 0, and for example, omega 3 equal 1. So how the model will look like? So it will be x1 squared plus x2 squared plus b equals 0, correct? x1 squared plus x2 squared plus b equals 0, it's the equation of circle, right? So it will be like this one. So I used, so I have, but in fact, I didn't use it like this here. I used only x1 squared and the x2 squared. So, so in this example, so you can do it like this one using 3 inputs, and imagine that omega 1 and omega 2 will be close to 0 or almost 0. So, and omega 3 equal 1. So the equation will be x1 squared plus x2 squared plus b equals 0, which means omega 1 squared plus omega 2 squared equal minus b. You can just say it's equal minus r squared. In fact, this is an equation of a circle, right? An equation of a circle, correct? You can make it more simple. You can instead of using, you can just make it more simple. In fact, I can just use x1 squared here and the x2 squared. This one is omega 1 and omega 2. We have bias. So the model will be omega 1 times x1 squared plus omega 2 times x2 squared plus b. It's the same. If omega 1 equal omega 2 equal 1, it will be exactly a circle. If omega 1 and omega 2 is different, it will be oval, correct? So it will be like not a circle, not exact circle. So in this case, I used this one here in this example, and I got omega 1, omega 2, both equal, and this is bias value. And so this is the equation of the circle, in fact. This is the equation of the circle. And then when you generate the value for x1 and substitute it for x2, you can get the exact circle. So now the decision boundary, it's a circle. All data points which are located inside, it's +1, and all data points outside it, it's 0. So now we can simplify it, right? So feature construction or feature, I mean, working with features, working with data pre-processing, it's very, very important. It will make life, but of course, it's not easy. You should expect that you will spend the time with it. But we are lucky, in fact, because there are some tools which can do this for us. We can automate this process, in fact. But the idea behind it, it's simple. It's just using those features. We try to multiply those features, use higher order features, try to generate new features. And after that, we will check which one is best. Which one should we keep? Which one should we ignore? Right? So feature construction, very, very important. Feature engineering, I mean, is very, very important. Okay. Okay, we need a break?
Yeah.
I think you also need to update the screen that they are seeing.
So they are not?
We can see it. Yeah, we can see it.
You can see.
No, but on
on the screen share, you can see it.
it's not the same. It's 2 slides behind.
Okay, so we will take break, and we will take break 10 minutes. You just get your coffee, and also people online, please just take your coffee, and we will meet after maybe 10 minutes. So also we will try to fix this camera and stuff. Thanks.